So, hello everyone, we are from Team 8. So, we are going to demonstrate our project implementation of load balancing mechanism for heterogeneous clusters. So, these are the contents of our project. Background. Cloud computing has transformed the way we utilize computing resources, enhancing both scalability and cost effectiveness. As the demand for these services increases, many organizations are adapting hybrid clouds that combine public and private clouds for better management and scalability. Modern applications like IoT and AI require substantial computing power. To accommodate this, our cloud environments use GPUs and FPGAs in some nodes to boost performance. This has led to formation of heterogeneous clusters where nodes vary in their hardware capabilities like CPUs and GPUs to handle specific workloads efficiently. However, this diversity introduces significant challenges in resource management and load balancing. Next slide, please. Motivation. The motivation behind developing dynamic load balancing strategies for heterogeneous clusters is driven by the inadvocacies of existing methods and rising adoption of these systems in contemporary cloud computing architectures. As organizations increasingly opt for hybrid clouds to leverage the advantages of both public and private clouds, the complexity of managing these environments grows, and resource management and load balancing in heterogeneous clusters is challenging. This motivates us in developing dynamic load balancing strategies for heterogeneous clusters. Next slide, please. Problem statement. Traditional load balancing methods face significant challenges in managing heterogeneous clusters in modern cloud computing. These methods often assume uniform server performance, use static configurations, and fail to adapt to real-time changes, leading to poor resource allocation and inefficiency. Additionally, uh, they typically measure server capacity with a single metric, which can misrepresent true performance. So these limitations underscore the need for dynamic, adaptable load balancing strategy that can effectively respond to diverse and changing demands of heterogeneous clusters. Our research focused on evaluating these issues, demonstrating the necessity for dynamic solution and developing new strategies to improve cloud resource management.
Load balancing is very important for using resources efficiently in clusters with different types of servers. Traditional load balancers like IPVS, maglev, HAProxy, and Nginx use simple algorithms like round robin, least connections, and weight based distribution. Like I just want to give a brief intro about these load balancers. IP Virtual Server built into the Linux kernel. It supports algorithms like round robin and least connections. Maglev is a load balancing technique developed by Google, and also it uses the consistent hashing to spread traffic evenly across the servers. HAProxy will work at the network and application layers. It allows setting weights for server manually. Nginx is a web server that is primarily used for web applications. These algorithms don't adapt well when server performance changes or like the workload change or when the servers have different capabilities. For example, IPVS allows you to set weights, but these weights are fixed and cannot be changed automatically. When maglev spreads traffic evenly, but it doesn't consider that some servers might be more powerful than others. HA proxy lets you manually set weights, but you have to do it by yourself. Nginx is more focused on web traffic. So researchers have tried to create smarter load balancing that can monitor server performance and also the traffic patterns. But we still need to understand if this complex solutions actually performs better than the simple ones. Our project wants to test existing load balancing methods on a realistic cluster with different types of servers and workloads. We also want to create a new load balancing system that can automatically adapt to changes in the cluster.
Okay, so we have a few goals when it comes to how our research is conducted. First of which is to accurately model a heterogeneous cluster. And this is important as it gives us an accurate testing environment. Next, we want our system to resemble real-world systems. And in order to meet this goal, we use IPVS, which is used in real-world load balancing applications. We also implement a custom TCP and TCP client and server to impart a load on the system. And we use valuable metrics which reflect the performance of the load balancing scheme on the heterogeneous cluster. And ultimately, this provides us with a realistic test bed. VirtualBox is the tool we use to replicate the nodes in the system. We use 3 VMs, each of which are running a current version of Ubuntu. One VM acts as a director which receives client requests. The other 2 VMs act as real servers which carry out the client requests. And most importantly, the real servers are customized with differing hardware capabilities. And this is again to accurately represent a heterogeneous cluster. So we achieve server load using a custom TCP client and server. The client makes concurrent requests to the director via the virtual IP and collects performance metrics. The server receives client requests from the director and carries out a response. And both the client code and server code are multi-threaded to enable concurrency. So we chose performance metrics that are impacted by load balancing strategies, as we want to understand the functioning of the strategies. Average response time and throughput are used because they are important to users who require the available services, and they're calculated as follows. Response time is equal to the time a response is received minus the time at which the request was sent. And throughput is calculated as the total amount of time taken to handle every concurrent request divided by the number of concurrent requests. All right, so moving on to experimentation details. Again, we're using an IPVS load balancing scheme on a heterogeneous cluster, and this is comprised of 3 VMs. So looking at this diagram, you can see how it's laid out. The director resides in VM0, and the concurrent client requests reach the director through the virtual IP. The director uses IPVS to determine which real servers the requests are sent to. We use a tool called IPVS ADM to configure the Linux virtual server. And we designate VM0 with a virtual IP, and we configure VM1 and 2 to be reachable through the VIP. And this also allows us to choose a scheduling algorithm like round robin or weighted round robin. Our initial testing is done to show why a dynamic load balancing approach is required. Round robin is compared to weighted round robin with VM1's weight set to 3 and VM2's weight set to 4. and this weighting is chosen to reflect the hardware capabilities of the VMs. And finally, an increasing amount of concurrent client requests are made to introduce a load on the system.
In our initial experiment, we compared two load balancing algorithms, round robin and weighted round robin. Round robin distributes requests equally across all servers, while weighted round robin considers the different capabilities of each server and adjusts the distribution accordingly. So, what we tested this with servers that have different CPU power. The servers were running tasks that use a lot of CPU. The results showed that weighted round robin performed better than the simple round robin. This is important because it shows that conjuring several capabilities can improve performance. Actually, there are two main reasons for a weighted round robin better performance. It sends more requests to servers with stronger CPUs based on their assigned weights. Since our tasks use a lot of CPU, using the powerful servers more efficiently, like it will lead to a better overall performance. In a real scenario, we may not know exactly how powerful each server is when setting up. So also this cluster load can change over time as more servers are added or like the request coming in change. So to handle these changing conditions, we need a load balancing method that can adapt to the cluster load and also the server capabilities in the real time. So as we can see from these graphs, the weighted round robin approach outperforms round robin in terms of both throughput and average turnaround time. But we believe that a dynamic adaptive load balancing strategy can further improve these metrics by responding to changing conditions in the cluster. Moving forward, our main goal is to create an adaptive load balancing system. This system will monitor the cluster and workloads in real time. If condition changes like new servers added or different types of tasks, it will automatically adjust by itself. Current load balancers use fixed settings, but in real time, when network conditions and workloads can change over time, then an adaptive system can respond to these changes. Our research will focus on designing adaptive algorithms that can detect changes in server capabilities and also upload the load distribution to make best. So the main goal is to ensure efficient load balancing to uh, no matter what servers or like task we have. This adaptive approach can improve overall performance and a real reliability of applications, mainly running on these clusters. Thank you.
Okay, I'm just going to do a quick demo showcasing how our experimentation works. So we have the three VMs. The VM on the left is the director, and the other two VMs are real servers. Each of the real servers is running an instance of the server program. First thing I have to do is configure IPVS using IPVS ADM. I've written a script to handle that for me. You can see the output. Um, we're making the director's IP, which is 10.0.0.54, available as a virtual IP. And that virtual IP points to the real servers at 10.0.0.236 and .239. And we can also see that we've designated the scheduling algorithm to be round robin. Next, I'm going to show you the experiment code. So we're basically just going to loop for 5 times, and each time we're going to request more and more concurrent client requests. So we'll start out doing just one request, and then 2 concurrent requests, and then 3, all the way up to 5. So I'm going to run that. Okay, that's done. So now I'm going to save the results to another file. And we can run the setup for round robin, which looks pretty similar. We have the VIP, which points to the real servers, but instead of using round robin, we're using weighted round robin. And there are weights applied to the real servers. So one real server has a weight of 3, while the other has a 4. That's due to the hardware differences. The server at 10.0.0.239 has more CPU cores available, so it should run faster. I run the experiment again, and that's done, so we can save the results. Now let's look at those results. Okay, so we have the results for weighted round robin on the left and the results for the regular round robin on the right. It's kind of hard to tell from the output here, but the weighted round robin's performance is better, which leads us to believe that a dynamic load balancing solution could be better than these static approaches. One more thing about the setup is it's very flexible as it uses IPVS, and some of our references show that a dynamic approach can be applied to an IPVS load balancing scheme.